movement, lots of excitement, lots of people moving around, so all of a sudden session 22 can get started. Would like to pick up last class where we left off, talking a little bit about curing of concrete. So if we go to the slides, you'll remember that we were talking about curing of concrete, and we were up to the point where we were discussing the ever-exciting topic of plastic shrinkage. And we were talking about the idea that over time, the cement particles are going to be sinking down, the aggregate particles are going to be sinking down, and the water is going to be rising to the surface of the concrete. And as that water starts to rise to the surface of concrete, you'll hear people refer to this as bleed water, or the surface will actually get a sheen. Sometimes you'll hear people talk about the sheen. This means that the surface is shiny. The basic idea here is this water is there. It will evaporate off. This water, if it evaporates off, it's essentially just taking water away from the surface and not really drawing the water out of the structure of the concrete. If the evaporation rate gets too high, though, you'll start to see this water front receding in between the particles, and there you can start to have a problem, because what you're actually going to be doing is generating a very high underpressure in this pore fluid, and that high underpressure could result in cracking. So the basic idea is if the bleeding rate is greater than the evaporation rate, you don't really have a problem. If the evaporation rate is greater than the bleeding rate, then all of a sudden you can start to develop high levels of stress. And that stress could be calculated from the equation given here, where the capillary stress in the liquid is given as negative 2 times the surface tension at the liquid vapor interface. For water, this is something around a value of about 72 dynes per centimeter. And R is the radius of the pore. Now this, you have to take some approximations, but this is basically the size that's between half the distance between some of these large particles. Now this leads us to a fairly famous nomograph, and if you've never had the opportunity to use a nomograph, these were very wild and exciting in the 20s, 30s, 40s, and 50s. This one here traces itself back into about the middle 1950s and really starts to try to provide an estimate of how you can estimate how fast the water is going to come off or evaporate off the bleed surface. So the basic idea is it tells you sort of how fast water is going to be leaving this surface and gives you some good rules of thumb on how it's influenced by the environmental conditions. This comes out of a paper by Menzel, and it's actually, I've been asked to give a review of the paper by Menzel, and the original paper is kind of an interesting paper, because the first half he sort of talks about this nomograph, then he kind of talks about a few jobs he's been on in his life, and then the paper looks like it ends. It just sort of drops off into sort of obscurity, and the paper is probably one of the most fundamental papers that has changed the way that concrete construction takes place. Here the basic idea is you're asked, this will be in the ACI hot weather concreting, cold weather concreting. The nomograph appears a lot of different places. PCA, it'll appear in your design and control book, it'll appear in your textbook, and this nomograph comes out, and the basic idea here is they tell you, consider it's a summer day, the outdoor air temperature is 80 degrees Fahrenheit, the outdoor humidity is 60%, so these are things that you could be getting from Channel 19 or Channel 6 or the Weather Channel, or your iPod, or asking a friend, or reading the newspaper, whatever it is that you're using to get that information. Concrete temperature is 100 degrees Fahrenheit. The wind velocity is 10 miles an hour. And what it tells you to do is to go to the nomograph and estimate the rate at which water evaporates. Now, one of the things that I will tell you that's kind of a little known fact about this graph is this graph has very little to do with concrete. This graph is how fast water evaporates off of the surface of some lake. All right, but the basic approximation that Menzel made was he said, bleed water on the surface of concrete, it's a lot like a lake. And what we're going to do is we're going to assume that if we can predict the evaporation rate off of the surface of a lake, we can get it off of the surface of concrete. So you would enter this graph, and this red line doesn't appear on the nomograph, and you'll actually find that the nomograph doesn't appear in the beautiful Technicolors that I've reproduced it here. But you would come to the graph, you would enter at the top of the graph up here, You would enter with the air temperature. You would drop down until you hit the relative humidity of the air, which again was 60% relative humidity. You would come across to the concrete temperature. Again, drop down till you get to the wind speed, come back across, and it would tell you the rate of evaporation in pounds of water per square foot per hour. So this gives you an idea of how much water is being lost in terms of pounds per square foot of surface area of the concrete per hour. Now, one of the things that I will point out is anytime you are in this yellow region, you are encouraged to take caution. That's a big region. Okay, and take caution is kind of one of those things, it's like be safe. You don't really know what you're trying to be safe from. But basically, you want to take steps here to try to minimize the potential for cracking. Obviously, the higher you get, the closer you get to ringing the bell for plastic cracking to occur. Some of the things that you can start to walk away with here, you know that the drier the concrete is, the bigger the potential you're going to have for a problem. The hotter the concrete temperature is, the higher the wind speed, the greater the chance there's going to be a problem in this particular nomograph. Now, one of the things that I will point out is that this nomograph only tells you about the rate of evaporation off of the surface of the concrete. And there is a pretty wild dance going on here because you've got evaporation taking place off of the surface of the concrete, but every mixture is going to bleed water at a very different rate. So what's going to happen is while water is being lost from this surface due to evaporation, due to the wind speed, the temperature, the things that we were talking about previously, additional water is going to be coming up out of the concrete. All right, so that's part of the overall process. At the same time, the system is starting to react, starting to harden, starting to become more viscous. So you really have a wild dance that's going on between the evaporation, how fast the bleed water is replenishing the surface, how fast the system is setting up, and what type of autogenous shrinkage is taking place inside of the system. So it's not just as simple as controlling the bleed rate. However, this nomograph is very valuable because it gives you an idea, gives you a first measure, gives you a first assessment of if you're in a problem where you've got a lot of water potentially that's likely to leave the surface of the concrete. Now, I mentioned that the evaporation rates, the evaporation effects are going to be primarily up at the surface. We talked a little bit about the idea that fibers can be mixed into the system, and one of the things that I will mention, especially coarser fibers, will tend to increase the evaporation rate, typically because they're drawing more water to the surface, they're putting more water up there, you got more water to potentially leave the system. All right, other things that I will point out that we should take place, the lower the water to cement ratio in these mixtures, you may think, well, that's a great thing, we've got water out of the system, there's less water to shrink, there's also less water to bleed to the surface. All right, so now all of a sudden you've got a mix where there might not be any water coming up to the surface, but evaporation is still taking place. All right, these systems can even undergo something called autogenous shrinkage, which we'll spend a lot of time on later in the semester, but it's shrinkage that's basically kind of like a cannibalistic shrinkage. You run out of water in the system, and it starts drying out internally. All right, so here are some typical measurements of this. These are measurements, non-contact laser measurements to measure that shrinkage. You can see when you have a high water to cement ratio, the volume stays relatively constant. 50 microstrain amongst friends is almost nothing. All right. When you get to a lower water to cement ratio, you can see that the concrete's going to set somewhere around in this yellow box. Once the concrete undergoes final set, it's going to suck that water back in from the top surface. That bleed water that was up on the surface is going to be sucked back into the system, and the concrete is going to start shrinking dramatically. And you may have something that's 200, 300, 500, 1,000 microstrain taking place during the first 24 hours. That's a big deal, and that can lead to cracking. All right, there have been studies in Japan that have shown even concrete that's completely underwater can undergo enough autogenous shrinkage that it can crack. So you can completely be ponding a concrete, have it completely underwater, and it can still crack because internally it's drying out. The basic idea is it's drying out internally faster than the water can get sucked into the concrete. So these are some things that you need to be worried about, especially when you get to very low water to cement ratio mixtures. Now, what are some of the things that you would do? I sort of jokingly said it tells you to take caution, but doesn't tell you much of what to do. Here is the list of what you do. Right? Good concrete practice. This was another thing that that Menzel was able to do in his paper. He was basically able to describe why good practice is what good practice is. He used that nomograph to show that if you dampen the subgrade, it's less likely for water to leave the system through the subgrade itself. It's more likely for the system to stay wet at the bottom. More water is going to come to the surface. You're going to have more bleed water. Use a vapor barrier. Protect the concrete from losing water. Don't work in the direct sunlight. Right here, if you're working in the direct sunlight, higher potential for the concrete to heat up, higher evaporation. Reduce wind. Now, obviously, few of us have the powers of Evan Almighty to go out and hold up our hands and stop wind. But one of the things that you can do is you can put up windbreaks. So you can erect small walls to sort of keep the wind from hitting the surface of the concrete directly. You can basically work in a direction where you've minimized the effects of winds. Increase the number of finishers. This is essentially the same as asking your finishers to finish faster. Get it finished, get your curing compounds on, get your water on top, go as quickly as you can. Cover curing the concrete. Obviously, that's as easy as it sounds, placing something over it. You cut down on the evaporation rate. Night placement, you tend to have a lot less wind. One of the things that was incredibly enlightening to me a few years ago, we had the opportunity to watch several construction sites where we were looking at saw cutting. And one of the things that was amazing to me is in Indianapolis, about the worst times for wind during the summer are between about 3 and 7 o'clock at night. And it's amazing. Almost every single day the wind kind of picks up, and then the wind seems to go away when it gets a little bit cooler at night. So you want, these are also things that you can measure now on site fairly easily. You can go to your friendly local Walmart and pick up a local weather station anywhere from like $30 till you can go for the deluxe model at Walmart and drop $68.50 or something like that, and get something that logs your time, temperature, all those types of things, which can give you a real good indicator. But there are pocket versions of this that are small as like a PDA, small as a Palm Pilot, something like that, that you can go out, get a pretty quick indicator of what's going on and whether you need to be worried or not for your particular application. The other thing, fibers will lessen some of these effects. As I mentioned, fibers will tend to stiffen up the system. They'll also tend to make it less likely for the system to crack. Specifically, the fibers that work the best are the ones that our friend the spider here is sort of hawking, is sort of telling us we want to buy. These are fibers which tend to have a very high fiber count. So sometimes you hear Martha Stewart on TV, now that she's out of the pokey, telling us a lot about all the different types of things she's selling this week at Kmart or Walmart or Target or wherever Martha Stewart sells all of her stuff. And she'll talk about finer fabrics. And when she's talking about finer bedroom sets, how does she let you know that they are good, fine linens? Thread count. All right, so those of you who haven't yet had the opportunity to go on a mission of picking out different types of sheets that have different thread counts and trying to look like you're enthused during the entire process, all right, you will get that opportunity at some point. All right, thread count is akin to good quality linens. When we start talking about fibers, we're really looking at how small the fibers are, how well they're distributed throughout the system. Now, one of the big problems is we want big, coarse fibers to bridge the cracks when they start to form because they're going to provide a lot of stress transfer. But we want a lot of fibers to help with things like stiffening the material while it's in a fresh state or creating places for water to wick to the surface. If you have a lot of fibers with a lot of surface area that go into the mixing process, it can become a real problem and the fibers won't mix in very well. So one of the things that people try to do is they try to get fibers that open up during mixing. So they may go in, they may look like a hockey puck, and then at some point during the system, the hockey puck kind of explodes and shoots fibers throughout the entire mixture so that they mix in slowly over time. Here you can see an application where the single fiber will actually start to open up and it will look like this spider's web because they've essentially sliced the surface of the fiber. So it goes in, it looks like one fiber. During the mixing process, it kind of unravels and opens up this mysterious thread here, or this mysterious spider's web, to try to create as much surface area for that particular fiber as possible. Here you can see some different work that was done. This basically shows that not only when we increase fiber volume fraction in the Z direction, not only do we start producing cracks that are smaller, but we reduce the probability of cracking, we drop down the number of sites that cracks are going to happen, and we reduce the average crack width, which can be a very big thing. So one of the things that we will talk about more when we start to talk about the impact of crack width on transport, it's been estimated that about 95% of the stuff that flows through a crack flows through the biggest 5% of that crack. So the majority of what's controlling what's going through that crack is the biggest portion of the crack. And a lot of times we want fibers to try to reduce the big parts of the crack. We go from something like 1.2 millimeters down to something like 0.5 millimeters. Make the wider parts of the crack much narrower. The flow rate through a crack scales as the width of the crack cubed. So here, if we drop the crack in half, we don't necessarily drop the flow rate in half. We drop the flow rate down to something like 1/8 of what it actually was. And believe it or not, we'll actually spend some time later on talking about where that number comes from. So you'll be able to prove it to all your friends, win bar bets, and all those exciting things. Anybody excited about that? One person's going to win a bar bet with that. All right, we've talked a little bit about the influence of temperature. I'm not going to spend lots of time on the influence of temperature here. Obviously, the hotter the temperature, faster it's going to set. One of the things that you can do is you can figure out ways, if the concrete itself is too hot, how you will cool down the initial ingredients. So here you can see cases where they are replacing liquid water with a different phase of water, this ice. They're making the concrete a great big icy or slurpy, depending upon your particular interest. They're cooling the ingredients. Here they're using liquid nitrogen. They may be actually just wetting the aggregate pile, using sunshades, screening the system. The basic idea is if you can cool down the aggregates, cool down the cement, cool down the water, you stand a high probability of making the concrete temperature much cooler. And there's going to be limitations on how hot the concrete can get before you start to place it. And depending upon where you are, those limitations are actually going to change.
Can you cool it down enough to affect the rate of reaction?
Yeah, they will be cooling it down quite a bit. Here you can be dropping the temperature 15, 20 degrees Celsius. And you're doing it before it gets back into the back of the drum. One other thing that I'll mention here, for a while I did quality control for the state of Pennsylvania, and one of the companies that we worked with had the nicest concrete trucks you've ever seen. They were dark black. And during the summer, those trucks had concrete that was hotter than any other concrete around because the drum was absorbing the energy from the sun. So they would actually bring the trucks back, and they would put the trucks themselves under a sprinkler system to cool down the drum. You'll notice if you drive down towards Indianapolis, there's about 3/4 of the way down on the right-hand side, there's a concrete plant that sits back in there. One of the things that I find fascinating about that one is they've got every truck looks different because they're all painted with different color schemes, and they all have numbers on the doors. So I don't know where they're racing those concrete trucks at night, but they all look like NAS trucks. So there's like a new series that's starting up, but I imagine they have a lot of temperature variation between those trucks as well. So as we mentioned, liquid nitrogen, ice, refrigerated water are ways that you can cool down the temperature of the individual constituent materials. You can cool down the heats of hydration with retarding admixtures and supplementary materials. There are equations here that basically give you the weighted averages, so the mass of the different materials that are going in, the temperatures they start at, and they'll give you an idea to estimate the temperature of the concrete in your mixture if you need something like that. Now, one of the things that I want to try to point out is that in modern concretes, modern high-performance concretes, this temperature rise that takes place due to the reaction can be pretty significant. This is a particular temperature curve looking at a particular concrete. This was taken in Austin, Texas, and I will tell you, I spent a few days in Austin one summer. I thought I was going to boil to death. While I was there, it was about 100,000 degrees, or maybe at least 110. It was very warm. I will point out that this particular concrete that we're looking at is concrete that's cast on a 70-degree day. So in Austin, you would say that's pretty mild temperature for them to be looking at. There's the heat spike that we see. This is obviously the heat of hydration. Temperature drops back down, and then we see some wiggling that accounts for seasonal variation and daily variation. But this is a pretty typical temperature development curve. Now, one of the things that is somewhat interesting, if we start to look at this type of curve, there was a bridge that was constructed, and John Myers and Ramon Carrasquillo looked at some of the temperatures that were developing inside of that concrete. And for those of you who are watching at home who don't have the benefit of the slides, I've conveniently cut off the fact that the y-axis is the temperature in degrees Fahrenheit. The x-axis is the time of casting in hours. And what I will mention here, again, as I've said before, 70 degrees Fahrenheit as your ambient temperature is a pretty nice day in many locales. It's not excessively hot. But when you start to look at the temperatures that are being developed inside the web, the flange, or the end blocks of this bridge element as it's being cast, you will notice that in the web, you're starting to see temperatures approaching 130 degrees, flange maybe a little bit higher. By the time you get over to the end blocks, you're looking at temperatures that are in the 190, 200 degree temperature range. Now, some of you will recognize that at 212 degrees, something magically happens to water. All right? It starts to boil, and we start to be able to make tea inside the pore solution of our concrete. So, I mean, we're getting to temperatures that are dangerously high here that can be doing things inside of our concrete. Now, one of the big issues that we want to talk about is the fact that if you are, and I mentioned this very briefly earlier on in the week, that a lot of times we take cylinders and we expect that cylinder to correspond to the strength in our actual concrete specimen. Well, here are results it's shown in black for the ASTM cylinder at 1 day and at 56 day. And if you look at this, you may say, well, at 1 day it was about 8 KSI, 8,000 PSI compressive strength. By 56 day, we had a really good concrete, 100 megapascal, 15,000 PSI mixture. This is a pretty good concrete. What you'll notice is when they cored the rest of the concrete slab, because of the rapid rise in temperature at early ages, they had way more strength than they would have had in the standard ASTM test. This is because there's higher temperatures, everything's good. At later ages, though, they don't crack 13,000 psi. They have substantially lower long-term strengths. And this comes back to the Tetris effect that I had mentioned earlier. The system is reacting so quickly that you can't fill in the microstructure as densely, and all of a sudden you start to limit the long-term strength. Now this starts to become a big problem, because if you're designing this concrete to be able to withstand 15,000 psi, and in the field it never gets there, you have dramatically under-provided what the concrete is going to be able to do in the field. So temperature management is really a major issue when you start to look at concrete elements. Other aspects of this that you might want to look at, there are places where we will steam the concrete. Here you're looking primarily at precast applications. What the name of the game, if you are making precast concrete elements, is to try to get the concretes in and out of the forms quickly so you can make some additional concrete elements. So one of the things that they will do is they will actually pump steam under a tent or steam through pipes in toward this concrete to try to raise the ambient temperature to make the concrete react faster. One of the things that you want to do is you want to make sure that we don't pump the temperature up too high, because if you pump the temperature too high, you can get alternative types of reactions taking place inside the system, things like delayed Ettringite formation or other types of reactions that can actually have a substantial long-term influence on the durability. So there are actually limits on the rates that limit how high the temperature can go, and also the rate at which you cool and the rate at which you heat and the rate at which you cool are all specified to try to avoid this. Now, just like we can have problems with the concrete getting too warm, here you see a concrete truck driver in the wintertime with his flamethrower out, because obviously, imagine a cold day. All right, here you can imagine a day where it's cold enough for the water in the system to freeze. Now this becomes a problem for a few reasons. One, obviously freezing water is going to make it very difficult for that cement and water to react and undergo the hydration reaction. The other thing is a real practical issue here, and as I mentioned before, this driver is going to go up and down on this truck several times. And he's spraying off the back of the truck with water. That water is hitting the back of the truck. Water, when it undergoes that phase change to become ice, becomes slippery. All right, and if this guy is going up and down this ladder, hanging off the truck a few times, there's a high probability that they can hurt themselves, and you want to really make sure that you've got good driver safety. Here you can see a windbreak constructed in the background. Here they are finishing the concrete on a cool day. What they're actually doing is the floor below, they are actually heating that so the heat is actually going through the concrete, coming up through the surface, and they can actually use the windbreak and the heat under the slab to be able to place this during the wintertime. One of the things that I will point out is we typically start to worry about cold weather when it's the average daily temperature is below 40 degrees Fahrenheit for 3 consecutive days. All right, so that is ACI's definition of cold. I like that definition. All right, my personal definition is about 70 degrees, below 70 degrees for 3 consecutive days is cold. All right, but ACI is maybe a little bit more realistic. Or it stays below 50 for more than half of any 24-hour period. Now, one of the other things that I want to point out here, and it's something that you won't hear a lot of people talk about, and on a lot of jobs you won't find out about this until it's too late, but here you can see a concrete pour. Let's imagine there's a pour going on inside here, and they're doing all the things right that they should be doing. They're heating up the air inside so that the concrete is going to set nice and quickly. One of the things that you will notice is that there's a place where you can no longer heat up all the air. All right, there's a place somewhere outside of this wall that they've created where the temperature in the air is going to drop back down and be cold, and that water that was forming is going to start to become a solid, and that solid is going to be our ice. A lot of times what you'll see is that you will create either icicles that are very dangerous, or you will create ice slicks right where everyone is walking and working. So you want to be real careful when you're heating the concrete or heating the area in a specific region that you're not creating something that's going to be dangerous for the workers in terms of creating a skating rink right in front of where they're going to be doing a lot of their movements or working, or a place where they're going to have projectiles being dropped off at them at regular intervals to keep them moving quickly. All right. One other thing that I'll point out as it relates to freezing, just because you design the concrete not to undergo a freezing environment doesn't necessarily mean that the concrete has never been exposed to freezing and thawing. You may have designed a concrete sitting in your lovely office in Miami. Now that the world of globalization has taken over, you may be designing something in Cleveland. And I will tell you that occasionally it's been known to snow in Cleveland. Once or twice, I think, in the history of mankind that has happened. You may have said, well, I assume that this is going to be constructed during July. Delays happen on construction projects. Once or twice that has happened in the history of mankind. So they may be putting that concrete out, and it may be exposed to freezing and thawing during placement. Frequently, you will see people entrain air in this concrete just for kicks, because it's going to help with the economics and because it may undergo a freezing at some point. Now, you can actually do things to insulate the formwork. Here are some examples of the R value, the insulation on formwork, and how much the temperature is going to maintain. Here are some different examples of that. Heating blankets can be used. For anyone who wants to see some of these, there's a pile of heating blankets in the basement of the civil engineering building. I don't know what they used to do outside to the poor students, but there is enough heating blanket down there to construct new buildings, I think. So, I mean, basic idea, just like you would want a blanket if you were sleeping outside, while the concrete's sleeping, it wants a blanket so it can retain some of the heat that's generated during hydration. Enclosures, we've talked a little bit about these. One last thing that I will mention about when you do, if you have to heat an enclosure, one of the things that you will notice is a lot of these internal heaters tell you to vent them properly. Venting them properly means venting them to the outside, and it is very common, especially on smaller types of construction jobs, for these not to be ventilated properly. If they're not ventilated properly, you are robbing the inside of oxygen, And people who may be inside like oxygen. You like oxygen. I like oxygen. It helps us breathe. While I'm sort of making light of this, this can actually be a very serious issue because people will all of a sudden start to have carbon monoxide poisoning. A little aside of this, Professor Scholler conveyed a story to me when I first started. For those of you who don't know Professor Scholler, he taught this class prior to me coming here, and he told me the story of going to a turkey farm, and the turkey farmer decided he was going to be nice to all of his little turkeys, and he built them a new concrete slab inside of their barn. He used one of these internal heaters to try to get the concrete up to temperature because it was a very cold fall. We wanted to get all the little turkeys ready for Thanksgiving. And one of the problems was he starved the air for oxygen. So they released these little tiny turkeys. I think there was something like 30,000 of them into this barn. And the little tiny turkeys had a great time eating the surface of the concrete because the concrete had never reacted because it requires oxygen to react. So the top surface of the concrete was this thing that would make Bill Cosby happy because it was a jello-like substance. The little turkeys were eating it. Little turkeys got sick, right, which was a big problem because 30,000 little tiny sick turkeys is a big, big issue. All right, so you want to make sure that you ventilate this properly, not only for the workers, but also the concrete surface to harden properly. Okay, we will jump forward a little bit, and we will start the next portion of the lecture. I fully anticipate that the discussion on quality control, material variability, and specifications will take us through the end of the class. Through the end of next class, so I'm not going to get this done in the next 18 minutes, but I think we can set up a good discussion of some of the issues that we're talking about when we start to talk about variability, quality control, and specifications. Obviously, if you were constructing a facility like this one that we see here, this is a offshore oil platform that's actually being constructed. It's being constructed in the fjords in Norway. It's going to be floated out into the North Sea. It's like the world's largest concrete canoe. They are then going to fill the ballast up with water. This thing will sink. It'll be about the size of the Empire State Building, and they will start pumping oil out of this and making the Vikings very happy because they're going to be selling that oil. And I don't know what the current price is, but they're getting about $90 a gallon for oil. 99? One guy who watches the oil price, right? Every day watching the oil go up and up and up. All right, so they're going to be able to utilize this in their oil drilling. Now, when you order something like this, you don't walk down to your local Menards and say, I'll take an offshore oil drilling platform, and please, if you could drop it off by Friday, that'd be great. So the question is everything going to be listed on the plans? And obviously not. There are going to be specifications or a written set of instructions. All right, so they'll tell you things about how this is to be constructed. When you're dropping something like $2 billion on the construction of one of these things, you can expect there's going to be a few pages that tell you how to make it. All right, we already know that there are specifications, and some places have put those specifications into song. All right, and for those of us who are old enough to remember, all right, there was a very catchy jingle that went out there to tell you the specification on making a Big Mac. Right? It said something about 2 all-beef patties, special sauce, lettuce, cheese, pickles, onions on a sesame seed bun. Now that tells you the ingredients, but it doesn't necessarily tell you all of the volumes. So you could go back through and you could start to add in the volumes. The special sauce, you're going to have 2 teaspoons of it, 1/4 cup of lettuce, a 5-inch sesame seed bun, and now we're starting to get close to mixture proportions and specifications. All should be right with the world, but in the early 80s, we know that there were 3 little old ladies who asked us the simple question, does the customer always get what they want? And here they were basically complaining about the fact that while the specification may be okay, maybe the specification isn't always followed, and you will remember that they were very impressed with the big fluffy bun. All right? And they were asking the question, where is the beef? Where is what I'm paying for? Did I get what I wanted? All right, now the question of concrete has been around for a long time. And before someone lets me know about the whole history of God and Jesus wasn't around, okay, I'm using this as an illustration, but I think since the beginning of time, there was some quality control that was taking place. All right, Genesis 1:25, God looked at his creation. He said it was good. It was good. He moved on and got paid. All right, so the first specification was satisfied. Now, a lot of contractors like this type of a specification. All right, most of them would like to take a step back and look at the dam that they've just constructed, declare it to be good, and move on to the next project. All right, unfortunately, not everyone is omnipotent, all right, omnipresent. So there are going to be other things that we do to make sure that the quality is there. There are other ways that we start to describe quality. If I asked you to describe what quality is, a lot of people would have a lot of different concepts here. We hear the phrase old world quality, and here we have Jurgen who's building some cabinets, and we know what old world quality is, but if I asked you to quantify that, it'd be pretty tough for you to do. A little old guy, a funny name, coming from the old country, doing something about as it relates to quality. So the idea of craftsmen and attributes and things like that is a little bit trickier. I will say that all of the discussion that we will have as it relates to quality, as it relates to concrete, comes from a little guy named Henry Ford. And Henry Ford completely changes the world's view of quality. So here we can see Ford with his Model T car in 1912, right? And the basic question and the basic thing that Ford really starts to put out is this idea that quality, especially when we start to talk about mass production, really doesn't have to do with declaring something to be good, really doesn't have to do with old world craftsmanship. It's really a reproducibility in size, shape, strength. He wants everything to be the same. Right? I believe it was Henry Ford who said that you could order a car in any color as long as that color was black. Right? He wanted every single car to be exactly the same when it was coming off the line. That's the same type of thing when we start to talk about the quality control of concrete. We are talking about quality control in concrete. Every batch has to be the same. Every truck having to be the same. All right, so the specifications are a written set of instructions for the contractor, all right, so that the owner describes what they want. Specifications are going to be designed to answer 5 key questions: what they want, how to order it, how to measure it, all right, what happens in the case that you don't get what you want, and how do you know if you got what you wanted. All right, the simplest type of these specifications we've talked about. It's the recipe specification. Make the concrete with these particular proportions. That's the first part of that specification. So an example of this may be something like the INDOT 402 or 502 specifications for concrete pavements. The concrete shall have a minimum cement content of 564 pounds, shall have a maximum water to cement ratio of 0.487, shall have an air content of 6.5 plus or minus 1.5%, shall be mixed for 60 seconds. Right? You could go through and you could do prescriptive specifications using this type of approach. The basic idea here is that the owner is going to make sure that the contractor complies with this. Right? If the contractor complies, they get paid and everyone is happy. Now, I will say that there are several steps in the process between specification and application. All right? And many of these steps can be variable. All right, so we could actually go back to one of the hardest jobs that's out there, and one of the hardest jobs is to make sure that you're getting exactly the same thing produced every single day. And to help us to try to keep in mind what every single concrete ready mix quality control specialist is dealing with on every day, we will break out the 18th or 19th century picture of our good friend Hans Areno. And Hans Areno was a water equilibrist. Now, some of you may say, that's a great job. Where do I get that? I didn't see that major in college. All right, Hans would set up these barrels, fill the barrels up with water, and he would make money by taking water and dumping it out of this barrel into this barrel into this barrel, and trying to keep his balance the whole time he was doing it. All right, we say that TV is boring today. This was a career. This guy was a superstar. He was the rock star of the water equilibrists. But this is essentially the same exact thing that we're asking a ready-mix producer to do every single day. We want them to look at the properties, the constituent materials, and the processing, and we're asking them to try to keep them balanced. Try to put all those things up on top of these empty chairs that are upside down and keep them all in balance Try to keep the variability low while maintaining costs as low as possible and quality as high as we possibly can. So variability is going to exist in every single step of the process. The question is, how do we minimize this variability, and how do we live with the variability that we have? How much variability can we accept, and what are the specific actions that we're going to take to start doing some process control? Now, as I mentioned, there are lots of steps in the process where variability can creep in. Specifications will tell you something about mix design and placement. The application will tell you what the properties are that are needed. But along the way, you've got materials, right? 4, 5, 7, 9 different materials being mixed in every single time. You've got processing, the aggregates being handled, the concrete being batched, it being taken to the site. You've got testing where you can have its own variability. So each one of these steps is going to bring in a little bit of uncertainty. Now, when we start to look at this, all right, one of the things that I will point out is the ASTM 169C, this was a book that's written by ASTM, started to ask the question of where does variability come from in some of these different material properties? Where does it come from in the constituent materials? All right? The admixture companies were good. They said we have very low variability. And the scientific survey said, yes, they have very low variability, because no one else said that there's a lot of variability, because they didn't even know how they would answer that question. All right. Aggregate has reasonable variability. All right. Reasonably low variability. Where you're going to see the bigger variability in aggregate is typically in your finer aggregates, especially as it relates to your finest modulus. It's going to show up there typically more frequently because you've got a lot more surface area that's coming on in the mixture. The survey says that fly ash, slag, and cement is the most variable. I would actually say that I don't believe that this is the most scientific of all surveys, because I think cement is probably the most tested of all the different materials that we use. And I think the cement production process is very, very consistent. I think what does change is cement coming from one place to another, and everyone thinking that all type 1 cements are created equally. You can have, depending upon where you're getting your materials from, either extremely repeatable supplementary materials or incredibly variable materials. And the main thing that we're looking out for here, fly ash carbon content will tend to be one of the things that varies the most. Steps in processing, obviously we've talked about all these handling, the mixing process, changing the times on the mixing, changing the way that it's dumped out, different operators, how they add the materials can make a big difference, the finishing process. All right, measuring, we can have different variability there. All right, and variability is going to come in each of these aspects. We've talked about where variability comes from, but really the big question here is, with the emphasis on reproducibility, how do we ensure that the concrete is reproducible as possible? Now, what I want to do is I want to try to give you a little bit of a picture of the big picture aspects of things that you should be worried about when we start to talk about quality control. Here, you're looking at not only just the concrete, but you're looking really at the general process, because some of you will go out to work at places where keeping or minimizing variability is going to be an important step in the process. If not minimizing variability, you will be asked to be documenting what you're getting. And mainly because if a problem comes up, you have to be able to document where the problem actually came about in the entire process. So you'll see things being saved like purchasing criteria, engineering drawings, equipment calibrations, pre, during, and post-pour inspections, the test results from constituent materials. All right, we have to keep records, all right, and we have to follow specifications. And we'll try to go through these in a little bit better fashion here. Purchasing criteria. Here we can see our favorite engineer, Dilbert, and here you can see Dilbert going through the process. And unfortunately, this is a process that's going to happen more than many of us would actually like on a lot of the operations. Here you can see him going through and asking for a discount even after all the contracts have been signed, and renegotiating the pricing. What I would say here is there's more to purchasing than just looking at the cost. You need to make sure that you're getting what's ordered, and you need to make sure that what's being ordered is what is being specified in the particular application that you're using. right? You need to set up a level of quality that you expect and methods that you can demand this from the people that are supplying this to you. All right, so you want to establish the specifications that you're going to be using, and you want to identify a procedure early on for what you do in the case where you don't have satisfactory materials. All right, so you don't want to wait until you've got 400,000 tons of aggregate on the ground that don't meet specifications before you start the process of negotiating what you do. You want to start the process of negotiating early on and saying, if I get bent bananas, we are going to send all the bent bananas back. All right? Because your version of what a quality material is may not be, and frequently is not, the same version as the person who is selling it. So you want to make sure that things are very clear from the beginning. What happens if what you send me doesn't meet my specification? You will take it back. We will not pay for it. We will pay for it at a discount. You want to make sure that that's clearly laid out from the beginning. Right? Double checking never hurts anything. All right, so here we can see our friends, the crash test dummies. They've checked things and still things seem to be going wrong. Right? But inspect materials when they show up. And I will point out a little tiny idea here. I will tell you that when I was a state materials inspector, if I pulled a sample from a truck, that got radioed back to the plant. As soon as I was taking a sample out of a truck, someone was back on the phone, back to the plant, letting them know, hey, there's an inspector out here who's taking samples of this material. Now, I am pretty confident it wasn't, hey, it's a good-looking guy out here taking samples. Hey, the engineer looks pretty smart. It was, hey, whatever you guys are doing back at the plant, somebody's actually watching you. All right? And I will tell you from being on both sides of that fence, if you are being watched, you pay a little bit more attention. So one of the things that you can do to just improve quality control processes to start is to pull samples. You will be shocked at how the level of quality increases just by taking the sample, whether you ever do anything with it or not. You will see that there's a lot more attention paid to the materials that come out. You want to make sure that you clearly mark the materials, identify what lots they're coming from, what trucks they're coming from, so if there is a problem, you can trace it down the road. Equipment calibration, you need to follow careful measurement procedures. You need to follow careful procedures. I will point out here, ASTM standards are standard for a reason. They are standard so that when everyone in this room does the test, we all get the exact same results. You need to make sure that the equipment that you're using is within calibration. It's calibrated on a regular basis. You need to check it against something so that you know the results that you're getting are correct. I will point out that one of the first opportunities I had when I came here 8 or 9 years ago was to put a cylinder, calibrated cylinder, into one of our testing machines and realized that we were actually measuring about 40% of what should have been measured coming out of the machine. That is a big issue. All right? You're getting strengths that are 40% of what you think they should be. You need to check this carefully on a routine basis. All right? There are procedures set up for how frequently you calibrate scales, how frequently you calibrate equipment, how frequently you calibrate the different materials. Whether it's internal standards that you're using, external standards, you need to make sure that the equipment is giving you reliable measurements. All right? You need to make sure that you do it as accurately as you possibly can. All right, before the pour, you should actually have a checklist that either you or someone that's working with you is going down and checking. They're checking for any spacers that are holding up reinforcing bars, any spacers that are holding blockouts, checking to make sure that the reinforcing steel has been installed. Armstrong Building, they had the opportunity to redo several of the pours in the footing because when they started to look for where the reinforcing should be in that particular building, they noticed that someone had neglected to put it in. Right? Reinforcing only works when it's inside of the concrete. All right? So you need to verify that the reinforcing steel has been placed. All right, verify the proper openings and sufficient bracings. Make sure that everything is in alignment. All right, check surface penetrations. All right, here you might have holes. Make sure they're in the right spot. Make sure they haven't moved around. All right, during the construction. You want to make sure you remind the crew of all of their duties. All right, during the concrete placing operation, where they're placing the concrete, who is vibrating. All right, you don't want all of a sudden when the concrete shows up, nobody thinks that they're running the wheelbarrow. All right, you want everyone to know what it is that they're doing, and you want to make sure that you discuss what you're expecting in terms of the concrete finish. Is it going to be a broom finish, hard trowel finish? You want to make sure that everybody's aware of it before it starts to show up. Now, what to record? Recording information is incredibly important, especially when you start to deal with trying to trace down problems afterward, or you start to deal with litigation. So what we are going to do next time when we start up class is we are going to talk about the fantastically exciting process of keeping records, keeping big binders of data, just so that you can go through them at a later point in time to try to figure out where a problem may have come up. All right, so we will pick up here next class period, and we'll take it from there. Thanks a lot.